Okay, welcome. So this is the first YouTube lecture we'll have. This one will be about an hour, since that's all that we would normally have allotted for Thursday's class. The second half of Thursday's class would be review for the exam, so we'll just do all of that through the WebEx meeting. So check your emails. I sent out instructions on that. We'll go over a little bit of the WebEx stuff, and then we'll start figuring out how to do like answering your questions, sharing screens, all of that kind of thing. So it's going to take a little bit of time to get used to stuff. I'd like to use some of the Google Drive tools, so you also received an invitation for that. So that's a place where we can share documents, notes, questions, sketches, etc. So we'll figure it out as we progress. This will become a little bit smoother, so just bear with me at the beginning. So what we're talking about are probability distributions. So essentially we have some event which is just generically now going to be called big X. So it's kind of like the big A or the big B or whatever from before. It's something we care about. So in this example, as we ended last time, X is how many consonants did we draw? So we're drawing 3 slips of paper with replacement, and each slip will have either a consonant or a vowel on it. So big X, the thing we're interested in is how many consonants do we have? So this big X is called a random variable because every time you select 3 slips of paper, it's random. The number of consonants that you will get is random. So the first thing to think about is, well, what values of big X could we have? How many consonants could we see in our 3 slips of paper? So as we established last time, that could be none. One of them could be a consonant, 2 of them, or all 3 could be consonants. And so what we have to do is, as we create this probability distribution, all that is this table. It's a summary table. What are the values of the random variable? That's a little x. Those are going to be numbers, something quantitative discrete for now. And then we need to know, well, what's the probability that the random variable, the big X, would equal that value? So for example, the first one that we figured out last time, what's the probability that big X equals 0? That's the row that we're in. So then as we translate that, what does that mean? Well, what that stands for is what's the probability, P, that the number of consonants we have in our 3 slips of paper, big X, is 0, little x. So we want to have 0 consonants. So when we think about, well, what do our 3 slips of paper look like? If none of them are consonants, well, then they all 3 have to be vowels. The first one's a vowel, and the second is a vowel, and the third is a vowel. So when we're finding the probability that X is 0, that's the same as saying, what's the probability that we get a vowel, and a vowel, and a vowel? And we know that we can just multiply all of these probabilities together because they're independent events. Nothing is changing because we're doing selection with replacement. So the chance that you get a vowel, there are 5 out of the 26 letters. So the first vowel, the second vowel, the third vowel all have the same probability. You multiply those together and we got 125 over 17,576. So that's what the probability of X equals 0 is. And we'll keep it like that. We won't simplify. So next we can look at something like, well, what's the probability that X is equal to 1? So what does this mean? Well, this means that in our 3 slips of paper, one of them is a consonant. So if we think about what that looks like, there's our 3 slips of paper. Maybe the first one is the consonant, and then we have a vowel and a vowel. So these have ands between them again. But this isn't the only configuration. The consonant could be anywhere in these 3 slips of paper. So we have an or. We have another option to think about. So the first one could be vowel, the second could be a consonant, and the third could be a vowel. Or, one more option, the consonant could come last. So we have a vowel first, a vowel second, and a vowel third. And again, between all of these, we still have the and. We're still going to be multiplying things. So the new piece here is that we have ors, so this means we're going to be adding all three of these probabilities together. And we're going to find them the exact same way. So let's start with this first one. What's the probability that we get a consonant, a vowel, and then a vowel? Well, the probability that the first slip of paper we draw, the probability that it is a consonant will be 21 out of 26. We put it back, we shake up the hat. Now we want to know what's the probability that the second one is a vowel. Well, again, we're dealing with independent events. The probabilities don't change. So the chance that we get a vowel is still 5 out of 26, and we're multiplying these, times the chance that the third one is a vowel, again, 5 over 26. So if we multiply that out, 21 times 5 times 5, so 525 is the numerator, the denominator will stay the same. So we have 525 over 17,576. So now we have to account for these other two cases. What if the consonant comes second? What if the consonant is, oh, I wrote this wrong, sorry. That should be a consonant last. So what if the consonant is second, or what if the consonant is third? And what we'll see is, well, nothing really changes. So we're going to add to this the next probability. So the chance that the first one is a vowel, 5 out of 26, times the chance that the second's a consonant, that's still 21 out of 26, and the third being a vowel, still 5 out of 26. So what you'll notice is we have the same numbers. We have 1 21 over 26, and we have 2 5 over 26s. And since we're multiplying them, we're going to get the same answer. So this is like saying 2 times 3 is the same as 3 times 2. The order in which you multiply doesn't matter. We end up with the same value. So we get another 525 over 17,576. Okay? So then, as you may surmise, well, we're going to get the same probability for this last outcome. We're going to use the same numbers, just in another order. So vowel first, 5 out of 26, times vowel second, 5 out of 26, times consonant third, 21 out of 26. But again, we get another 525 out of 17,576. So we've taken care of this first possibility, or the second, or the third. They're all the same value, so we just add them all together. So what you end up getting is 1575 over 17,576. And that's the probability that you would see one consonant in your 3 slips of paper. So we'll add that to our distribution. So the probability that x is 1, 1575 over 17,576. Okay, so one thing to look out for is check your probabilities along the way and see if it makes sense. Okay, so for example, we've so far have the probability that x is 0, that we have no consonants, and the probability that x is 1, that we have one consonant. So does it make sense that the probability has increased quite a bit? And in this case, yeah, it does make sense. So remember, this probability that x is 0, that's saying, well, what's the chance that we have no consonants in our 3 slips of paper? And keep in mind, 21 out of 26 letters are consonants. So we would expect to see quite a few consonants. It should be rare to have no consonants. It should be rare to have only vowels. That's why this probability is so small. Then, as we allow for one of them to be consonants, that probability should increase. We're more likely to see a consonant as opposed to a vowel. So we see this increase in probability. It seems okay so far. It's making sense so far. So then we'll just continue the same ideas for the remaining two probabilities. But I'm going to have to use a different piece of paper. So next we have the probability that x is 2. So same idea, what does this mean? The first step is like a translation. So we're saying what's the probability that in our 3 slips of paper the number of consonants we have is 2. So we have 2 consonants, 1 vowel. So what can that look like? So again, you think about your three slips of paper. So if you have 2 consonants and 1 vowel, it's essentially this, well, not the same, but it's very similar to when x was 1. So when x was 1, we had 1 consonant that kind of floated around between each of the 3 slots. Now we have 2 consonants and 1 vowel. So the vowel is the one that will be moving around. So maybe the vowel comes first, and then we have our consonant second and third. So again, these have ands between them. Or we could have a consonant first, the vowel could be in the middle, oops, and then the consonant could be third. Or the vowel could be the last one we draw. So we get a consonant first, and a consonant second, and a vowel third. So just like before, we have to find these probabilities, and again, they're going to be the same number every time. So let's think about the probability that we get a vowel, consonant, consonant. Not a very good notation. I should have put ands in between here. I'm just being lazy, I guess. So what's the probability that the first one is a vowel? Well, that's 5 out of 26. Nothing changes. Probabilities remain the same. We're doing selection with replacement. We know these are independent. We don't have to worry about conditional probabilities. We can just multiply them together. Consonant, 21 over 26. Consonant, 21 over 26. So our new probability that will be the answer to each of these 3 combinations. If we multiply those together, the denominator will still be that 17,576. So we have 5 times 21 times 21. So we have 2205 is the new numerator. 2205 over 17,576. So we'll just quickly go through the other 2 combinations, but just like when x was 1, we'll see that it's the same number, 2205. So for the probability of getting a consonant first, and then a vowel, and then a consonant, we'll have 21 over 26 times 5 over 26 times 21 over 26. And I'm not putting a sign in between these, but it's implicit that they're being multiplied. And again, we're going to get 2205 over 17,576. And then lastly, for the probability that we get a consonant and a vowel, same thing. I'll write it out just for completeness. So we have 21 over 26 times 21 over 26 times 5 over 26. And we get 2205 over 17,576. So the probability that x is 2, we have to take care of these ors, which means we just add these all together. So 2205 plus 2205 plus 2205 gives us 6615 over 17,576. Oops, couldn't see that, sorry. So we're just adding together the 3 probabilities, and we get the probability that x is 2. Okay, and again, this probability is larger than the probability that x was 1 and the probability that x was 0. And again, this makes sense. We should see more consonants. It should be more likely to have more consonants than vowels. So the probability of having 2 consonants should be somewhat large. and that's what we see here. So we can add that to our distribution. So now we just have one more probability to find. So there's 0, there's 1, there's 2. And at this point there are 2 ways to find the last probability. One is kind of shorter, the other one, well, it depends if it's shorter or not. But the one that's maybe takes a little more time, I would say you're more likely to get the right answer. So here's what I mean. So now we're interested in finding the probability that x is 3. So let's start with the easy way. Well, we know something about this distribution. We know that in order to be a valid probability distribution, all of these probabilities have to add up to 1, or in this case, 17,576 over 17,576. So we can use the complement rule to find the probability that x is 3.